In the technologically advanced landscape of 2026, where artificial intelligence scrutinizes every digital interaction, the A/B test has ascended as the gold standard for experimental validation. This process, however, relies not merely on the sophistication of our tools, but on the rigorous adherence to scientific methodology. The following narrative explicates the core pillars of robust A/B testing, revealing the precise mechanisms by which we separate statistical truth from comforting illusions. The journey begins with the conception of a valid experiment, in which the sanctity of the control and treatment groups is preserved. Imagine two parallel universes. In one, users experience the familiar layout. In the other, a key element is subtly altered. The critical challenge is to ensure these universes are indistinguishable except for the tested variable. Here, randomization algorithms act as impartial judges, preventing the insidious creep of selection bias. If demographic or behavioral differences favor one group, the experimental results are rendered moot, no matter how impressive the observed effect. This foundational step requires vigilance. Technical errors here propagate through the entire experiment, eroding any hope of trustworthy conclusions. Following experimental design is the discipline of hypothesis formulation. The rigor of A/B testing is found not in the arbitrariness of change, but in the clarity of prediction. The most robust hypotheses connect change to outcome via a logical rationale. For example, if we relocate the call to action button, then completion rates will rise because shortened visual paths decrease user friction. This is not mere guesswork. It is a testable assertion ready for null hypothesis significance testing. NHSD begins by presuming the new variant is no better than the current state, a humble intellectual posture, expecting no miracles. Only data with sufficient weight can overturn this presumption. However, a hypothesis is only as strong as the statistical certainty with which it is evaluated. Here, the calculation of sample size emerges as a non-negotiable requirement. Too often, teams are tempted to declare victory or despair based on an early glimpse at the numbers. This is statistical folly. The propriety of sample size hinges on two parameters: the minimum detectable effect, MDE, expected, and the statistical power, typically set at 80% or 90%. If the cohort is too small, the experiment becomes underpowered, a scenario where real effects escape detection and innovation stagnates. Pre-calculation of sample size ensures each test is invested with the capacity to reveal genuine insights, not mere statistical noise. Even after an experiment is technically and logically sound, interpreting the results introduces new hazards. The peaking temptation is notorious, monitoring the test's daily arc and halting as soon as success gleams on the horizon. This impulsive approach dramatically inflates the probability of false positives. The transient allure of novelty can further mislead analysts, as users engage with change simply because it is new, not because it is improved. Deeper statistical paradoxes, such as Simpson's paradox, remind us that aggregated results can obscure underlying trends within data segments. Only by squinting through these layers of complexity can one reach an unbiased understanding of cause and effect. Finally, the pace of modern experimentation calls for advanced techniques like sequential testing. In high-velocity environments, waiting for a fixed sample size can bottleneck innovation. Sequential testing offers a mathematically principled solution, allowing interim data analyses and potential early stopping, without sacrificing statistical integrity. By adopting this framework, organizations can maximize their testing throughput, surfacing high-impact changes while curbing the proliferation of false positives.